we're going to see a phenomenon here. It is much harder to see than when the sun has moved, so it's actually hitting the facade than right now. But you will still be able to see it if you look very carefully. So what I want you to do, like I said, you have to come close and personal, and there's a couple of places along here you can see it, is kind of get underneath the eaves here. Well, you'll see something that might be a little bit surprising. So try to move back and forth right along that pipeline there, right along the line of the building, on the inside where the pipes contact the building, and see if you see what I see. They are uneven, which is a very interesting architectural choice and a decorative choice. What else do people notice?
Omega.
Omega, yes, exactly, the last letter of the Greek alphabet, which we use for many different things in mathematics and in electronics. What else? If you go back and forth, if you're like me, I think you will catch a slight glimpse of the blue sky between the pipes and the building. Okay, so if you go back, you should be able to see little glimmers of light. This is why I say when the light is in front of the building, it's much more vivid, and you see it very clear. But I think you should still, even this time of day, be able to see slight glimmers of blue sky between the pipes and the building. Okay, why in the world would they leave space between the outer surface, essentially the outer walls of the building, and the rest of the building? Well, how does it? Okay, thermal expansion. Believe it or not, as incredible as this may seem, it sometimes gets cold in Dallas. What would you say is the lowest temperature that one might experience here in Dallas? 18 degrees Fahrenheit? Have you been here when it was 18 degrees? This year, 18 degrees Fahrenheit. You heard it right here. Awesome. And how about the hottest day in Dallas? What could the hottest day? 110. Okay, very good. So we could get a temperature differential of 110, sorry, I'm getting even more in, but 110 degrees minus 18 degrees is a temperature swing of 92 degrees Fahrenheit. Did I do that correctly? 92 degrees Fahrenheit. And one of the themes in middle school mathematics is linear relationships. It turns out there's a linear relationship between change in temperature and the expansion factor of aluminum. And that relationship is expressed by this lovely number, happens to be very convenient for aluminum, 0.0000123. That is the proportionality constant between change in temperature and the expansion factor of aluminum. So for 92 degrees, if somebody can quickly whip out their pocket computational device, also known as your cell phone, and multiply for me 92 degrees Fahrenheit by this number, 0.0000, 4 zeros, 123. That will give us the expansion factor of aluminum over a 92 degree Fahrenheit change. Somebody got that number for me? 0.00113. Okay, 0.00, let's do 3 decimal places. Okay, I think it was 0.0113. So we'll say 0.00113. So that is the fraction by which aluminum expands over a 92 degree Fahrenheit temperature differential. Okay, now, how tall is the building? We could do a whole math tour just on calculating the height of this building from different observations you can make. Don't have time for it. The building's 132 feet tall. How tall to the bottom of the pipes? Roughly, just guesstimate. 20 feet. So we got 112 foot long pipes. So 112 foot long pipes. Let's do this in inches. 112 times 12 is 1200 plus 12 times 12, which is 144, which I will always remember because what is that number called? It's called a gross. Isn't that a great name for a number? I got a gross of, I don't know, whatever. A gross of spiders. Yeah, I got 144 spiders. Oh, gross. Yes, that's right. It's gross. So what is it? So 1200 plus 144 is 1344 inches. 1344 inches. So now to find out how much it's going to expand, I'm going to multiply 1344 by 0.00113. Again, what's my total expansion? Somebody who's got that device, multiply 0.00113 by 1,344. 1.5. Okay, 1.5 inches. 1.5 inches. Now, that might not seem like a lot, But what do you think would happen if they bolted the bottom of this pipe to the building down here and bolted the top of the pipe to the building, to the top of there, and over the course of this year, where it's going to go from 18 degrees, what, a couple months ago, to 110 degrees this summer, what would happen? It would crack those bolts off like a toothpick, and we'd have huge pillars of aluminum crashing down on the theater goers. Not a good scene. So instead, what they have to do is create these flexible channels. They're linked at the top, but they're not linked anywhere below, and they're basically in a groove that runs along the side of the building to allow for that expansion up and down, because in fact aluminum is one of the more expansive materials, expands much faster than the rest of the building, and that's what keeps us safe as we go to the theater. Mathematics keeps you safe.